About the lecture, I should say a few words about IWM. So this is a collective of Indian women in mathematics, is financially supported by NBHM. So its purpose is to have a network of women doing mathematics, like research and teaching, and also make them aware of many of them from smaller places or thing. There are various career choices in mathematics other than research. So to do that, we across the countries run small regional workshops and also annual workshop, and also to have a showcase of prominent women mathematicians. We invite women mathematicians to give lectures, to choose one area or state of India, and they lecture in various universities and meet other women mathematicians. And in fact, incidentally, Rekha Thomas was supposed to do this this year. She kindly agreed after so many hurdles, but due to pandemic, this never didn't happen. So I hope in future soon we'll have when the things do normalize. So today's talk is the fourth talk in the series of visitor program lecture series. So Rekha, we have already given some write-up on Rekha, and on the poster you can see. But a few more things I would like to say is that she has authored a textbook on called on polyhedral combinatorics called Lectures in Geometric Combinatorics. Her area of specialization is optimization, mathematical optimization, computational algebra. So over to Rekha. I think talks title looks very interesting. At least it gives you a direct application of algebra. So we don't have to justify our grant. So okay, Rekha. So
Thank you, Vijayalakshmi. I'm going to try to share my screen first before I start.
yeah.
So let me go there. Okay. Can you see the screen?
Yes.
Yeah, we can.
Yes. Okay. I'm just going to put it in full screen before we go. Okay, great. All right. Is the screen visible now?
Yes, Rekha.
Okay, great. Okay, well, thank you very much. Thanks for inviting me to speak here. It's a really great honor to be here. I cannot see any of you, so if you have any questions, please feel free to speak up. I'll be happy to answer.
Sorry to interrupt. I forgot to mention, you can put the questions on chat box if you like. Also, or you can open your mic and talk to Rekha directly.
Yeah, either way. But I since the screen is in full view, I cannot see any of you anymore. So please stop and ask questions if you need it. Okay, so as Vijayalakshmi said, I work in optimization, but in the last 10 years or so, I have become sort of interested in problems from computer vision that use algebraic techniques. So either from polynomial optimization or from algebraic geometry. I'm not really an algebraic geometer, but as you see, we will need some of those techniques. So I want to talk to you today about a problem that we worked on recently that has to do with reconstructing three-dimensional scenes from pictures that you see in cameras. So this is something that's very used all the time, even in your phones. This is something that happens all the time. But we'll talk about a mathematical question that lies at the heart of these reconstruction problems. So that's what the talk is about. And you will see that there'll be a cubic surface that shows up. So this is joint work with several people. So let me show you my collaborators. Okay, so it's joint work with Samir Agarwal, who's at Google here in Seattle. So Samir and I have been working together for several years, like 10 years. We've had several PhD students together. And our latest PhD student is Andrew Pryhuber that you see in the middle. He's finishing his PhD in math at the University of Washington. And then we have a third collaborator from Germany, Rainer Zinn, who's a real algebraic geometer. So he was very helpful with all the real algebraic geometry parts of this project. Okay, so those are the people I worked with. And let me start right away by telling you what the problem is. So here is a very basic question that you can ask in computer vision. So suppose we're given a bunch of points, say U1 through UK in general in the plane. And we are also given another set of points, V1 through VK in the plane. So both are in the plane. So what you would like to ask is the following question. So given K point pairs, so UI, VI, they live in R2 cross R2. When are they the images of K points in the real world in two cameras? Okay, so that is the question. So in other words, what we are looking for is K points in R3 in our world, so that when two cameras take pictures of those K points, I get exactly these U's on one side and V's on the other side on the camera planes. That is the question, okay? So this is a kind of very basic question in vision, because what the question is really asking is, are there any kind of constraints among these U points and V points? Can I arbitrarily put some number of U points and the same number of V points on the other side? Can I just arbitrarily throw them down and expect to find some three-dimensional scene that actually gave rise to these two images? That is the question. And as you might guess, this cannot be arbitrary. And what we want to understand is what sorts of constraints do they have to satisfy, and is there a situation where you can always reconstruct, and will there be a sharp threshold at which you will not be able to reconstruct anymore, and so on. Okay, so this is the question we're asking. Okay, so to go on, I'm going to have to first of all tell you what a camera is, because the question was really, can you reconstruct under two cameras? And a camera in general, you should just think of as a map from R3 to R2. Okay, that is a camera. So for a mathematician, you can just think of it as a map from R3 to R2. And these maps can be quite complicated. So you can have nonlinear maps, you can have lenses with distortion that have complicated formulas. But for our purposes today, I'm going to talk about a model of cameras called projective cameras. So these are fairly simple cameras, and they generalize the pinhole camera, the usual pinhole camera. So let me explain to you how a camera works. So a camera consists of two parts. One is this blue rectangle that you see here. That is the camera plane. That's the viewing plane of the camera. There's also a center for the camera, which is this blue point that you see here. So the two blue things form the camera. And if I want to take a picture of a point like Q is in our world, and I want to take this picture, what you do is you draw the line segment that joins Q to the center, and you look at where that line segment intersects the blue plane. So this is this green point U that is called the image of the world point Q in this camera. Okay, so that is physically what has to happen. And there's also this pink ray here that's called the principal ray of the camera. That just is the perpendicular from the center to the image plane. So it's a perpendicular ray. And it's pointed in the direction that points to the front of the camera. And you will see that this is important, because cameras can only take pictures of things that are in front of them. They cannot take pictures of things that are behind them. And this will show up in a few minutes. Okay, so this is physically what a camera is. But now I'm going to write this mathematically. So mathematically, what a camera is the following. So it's a map. I'm going to call this map A. And to make things simple, it's always best to work in projective space rather than in affine space. So we're going to put this into projective space, and I made one slide to explain what projective space is, just in case there are some young people here who may not have seen it before, but bear with me for right now. So it's a map from P3 to P2, and it sends a point Q in three-dimensional projective space to just A times Q, that is the image. And this A times Q is called U, that is the image. Okay, so what is A? A is just a 3x4 matrix. So if you don't want to think about it in a complicated way, you can just think of this as a 3x4 matrix that sends a point Q that has 4 coordinates in it, because we're in P3, to A times Q, which has 3 coordinates in it, but you should think of it as a point in projective space of dimension 2, okay? And this matrix is not any matrix. The only restriction on this matrix is that it has to have rank 3. Because if it doesn't have rank 3, then what it'll do is it'll take the world and it'll collapse it down to a line or to a point, which we do not want. So we really want the camera to image the world to a two-dimensional plane. Okay, so a camera is just a 3x4 matrix of rank 3. That's essentially the definition of a camera for this talk. Right, so that's mathematically what it is. And the center, you can calculate what it is once you have this A. So the center is going to be the generator of the right null space of this matrix. So this matrix is 3x4, it has rank 3, so it has a one-dimensional right null space or kernel. And that null space is generated by some vector C. Again, we think of it as living in projective space. And that is exactly the center. And we say that the camera is finite if the center is finite as a projective point, okay? And the principal ray is also some vector, so we call it N. It's going to be a vector in P3. So that's the basics of a camera. So it's a 3x4 matrix of rank 3, and it defines this linear map that goes from P3 to P2. Good. Okay, so let me spend 1 or 2 slides just talking about what projective space is, just in case there's someone out there who may not have seen it before. If you're confused in the talk, you can always just think of Pn as Rn plus 1, essentially. But Pn, n-dimensional projective space, is just all the lines through the origin in Rn plus 1. That's basically what it is, okay? So let me say it a little bit better. So formally, what you do is you take Rn plus 1, which is affine space, you remove the origin, and then you mod out by this equivalence relation that tells you that 2 vectors are equivalent if they are multiples of each other. So if A and B are equivalent if and only if B or A is a multiple of the other one, okay? So in other words, an entire line maps to a single point in projective space. So here's a picture that I tried to draw. So here's a picture of P1, for instance. If I want to construct P1, what I do is I start with R2, which is the orange, the 2 axes in orange are depicting R2. And then every line that goes through the origin becomes a point in P1. So the green line is a point in P1, the blue line is a point in P1, and so on. So I just need to write down 1 point on the line to represent the line. So one way to do that is you draw this red plane, which is, say, at height 1, and then you just record where the red plane cuts the different lines. So this green point is probably some B, comma 1, the blue point is some A, comma 1, and so on. So I represent each line by 1 point on the line. So that's a point in projective space. And this way I catch all the lines that go through the origin except this orange line. The orange line will not cut the red line. So that orange line is called the point at infinity. And this orange line will have a 0 as the last coordinate. So there is that one special point, and then all these other points which have last coordinate 1, which are called the finite points. So when I said the camera center has to be finite, what I mean is this, that the last coordinate of the camera center has to be non-zero. It has to be 1, okay? So this is projective space. It's just lines through affine space in one higher dimension. So in this projective space, the vector 1, 2 in R2 is the same as the vector 2, 4, is the same as the vector -2, -4, and so on. They all lie on the same line. So that's P1. Here's P2. So we do the same thing. We start with R3. And then we draw we look at all the lines through the origin in R3. To represent each line, I create this red plane, which is at height 1. And I can just look at the intersection of all the lines with that plane. That gives me a representation of the point. And then you're missing all these lines that go through this orange plane, which is the horizontal plane in R3. So each one of these lines in the orange plane is also a point, but it's a point at infinity. And then all of these lines that go through this orange plane together form the line at infinity, okay? So that's like a crash course on what projective space is. If you don't know it, just think about it as Rn plus 1 whenever I talk about Pn, okay? But the reason we care about projective space, at least in this talk, is because we want to understand where homogeneous polynomials vanish, Okay, so I want to understand zeros or roots of homogeneous polynomials. So if I have a homogeneous polynomial, let's call it P, and let's suppose it has n+1 variables, x0 up to xn, then if it vanishes at one point A, then it'll also vanish at all multiples of that point, right? So for example, look at this homogeneous polynomial x squared y minus z cubed. It's homogeneous because both the terms have degree 3. So if it vanishes at one point, for example, it vanishes at the point 1, 1, 1. If you plug in 1, 1, 1 for x, y, and z, you will get 0. But it'll also vanish at every multiple of 1, 1, 1. So you don't want to think of all the multiples as different points. You just want to think of a single point in projective space as the 0 of this polynomial given by 1, 1, 1. Okay, so that is why we care about projective space in this talk, because we are going to see a lot of homogeneous polynomials. And if you want to understand their zeros or their roots, it's best to think in terms of projective space. If you vanish one place, you'll vanish on the whole line spanned by that point. Okay, so the last background slide I have is what's called a projective variety. So if I have a bunch of homogeneous polynomials, say P1, P2, all the way up to Pm, and they are in n+1 variables, I'm using the real numbers as my field, but you could use anything else. The complex numbers will show up shortly. But let's just do real numbers so that we can draw pictures. So if you have a lot of polynomials, you can look at their variety, which means the common zeros or the common roots of all of these polynomials. So I want to look at all the vectors z that live in Pn that vanish on P1, P2, P3, all the way up to Pm. Okay, this is called the projective variety of P1 through Pm, the common zeros. So here's an example. So I've just taken one polynomial, this big polynomial here. It is homogeneous of degree 3, and it has 4 variables in it. So its picture should live affinely in R4 or projectively in P3, right? So projectively, it lives in P3. And the zeros of it is this picture you see on the right here. This is called the Clebsch surface in P3. It is some complicated object. The reason we can see it is because we are cutting it with this red plane that I was showing before. So you can see a 3-dimensional picture of it, but it actually lives in R to the power 4, where we cannot see it, but it's filled with these lines. So we can cut it off and look at the 3-dimensional picture. Okay, so this is a projective variety, and we'll see some of these varieties. We'll see some very simple varieties in this talk. Okay, good. So let me come back to my problem. So I'm trying to reconstruct these two sets of points. So somebody gave me k points on the u side and k points on the v side. I'm going to record them in this set that I'm going to call P, this calligraphic P. So I'm given these pairs, ui, vi, there are k of them. And I always put them in projective space because everything works in projective space in vision. So the way we put this in projective space is we take our original ui and vi, which used to live in R2, and you just stick a 1 at the end. So we put them into P2. Okay, so you should think of these as 3-dimensional vectors with last coordinate 1. So if that's my input, this is going to be my input always. And first we can ask for a projective reconstruction of these points. Okay, so what does that mean? That means I want to find 2 cameras, A1 and A2, which means we need to find 2 3x4 matrices of rank 3. And I need to find k points in the world. So I need to find Q1, Q2 up to Qk in our world, such that when I look at A1 times Qi, I will get Ui. So that means the first camera takes a picture of Qi and gives me back Ui. The second camera takes a picture of Qi and gives me back Vi. This is what this means. And this squiggle here just means that they're equal in projective space, okay? So as projective points, this point and this point are the same, which means that they are equal up to scaling. So these are some algebraic equations, right? These are just linear equations in some ways. We want to write A1Qi as Ui and A2Qi as Vi. So this is a projective reconstruction, just finding 2 cameras and finding world points such that this happens, okay? So this is what happens, for example, in Google Street View, right? The Google car will go around and take pictures of your neighborhood, and then they reconstruct the neighborhood for you. And this is exactly what they do. Okay, this is not exactly what they do, but this is the first part. This is what's called a projective reconstruction. Now, projective reconstructions are fine. They are the first step, but they're not really correct, because if you projectively reconstruct like this, it could be that the world point is actually behind the camera. So when you only satisfy algebraic equations, you cannot guarantee that the scene is in front of the camera. So we need something more. We need to guarantee that the scene that you reconstructed, which is Q1 through Qk, is actually in front of the camera. So what we actually need is something called a chiral reconstruction. So chiral, for chirality from chemistry, you've probably heard this word before. So that stands for sign. So we really want something in front of cameras, which means that these world points that we found, they have to satisfy some inequalities. And there's a lot of inequalities here. It doesn't really matter what they are, but the main thing to notice is that they involve that principal ray, that pink ray that we saw in the camera that tells you which way is front. So N1 is the principal ray of the first camera, N2 is the principal ray of the second camera. So you need to satisfy this quadratic inequality for every Qi. Then you need to satisfy some more inequalities. This N infinity is the normal of the plane at infinity. So it's just 0, 0, 0, 1, okay? So again, what this exactly is not important. What's important is that they are inequalities. So we need to satisfy these equations as well as these inequalities. Everything is polynomial. So we end up with something semi-algebraic, meaning that you need to have polynomial inequalities as well as something algebraic, which means you have polynomial equations, okay? So what we really need are chiral reconstructions, and these are not very well understood. So in general, people haven't studied chirality very much. Usually people will do projective work, and that is almost completely understood. It is completely understood for 2 cameras, but not the chiral version. So this is what we're looking for. Let me show you a picture to show you the difference between these 2 reconstructions. Okay, so on the left here, you see a picture of a comb. That's a comb. And then on the right, you see a reconstruction that is projective, but not chiral. Okay, so it satisfies the algebraic equations, this reconstruction, but it does not satisfy chirality. It puts the comb partly behind the camera and partly in front of the camera. So it splits it across the principal plane, okay? So this second kind of reconstruction is not what we want. We want to put the comb entirely in front of the camera, and that's what we're looking for. So the question is, when is that possible? Okay. This particular picture is from this book by Hartley and Scissorman, which is sort of the standard book for all these geometric problems that come from vision. Okay, so this is the question. Good. Right, so before I get into more math, let me actually pause and tell you a little bit about the history of these questions. So this type of question is very old.
Can I ask a question, Rekha?
Yes, please, go ahead.
Which one, I mean, given a pair of endpoints, how do you know which ones to pair?
Oh, so the pairing is part of the input. It's given to us before. And it is actually a very difficult job to actually pair these points. So if you think of taking 2 pictures, so let's say you have 2 pictures of the Taj Mahal, one from one angle and one from another angle, then somebody would have already paired this up for you. So if you have like one corner of the building in one picture and the same corner in the other picture, you want to call them U1 and V1. You want to pair them up, right? And this is a difficult problem in general. So if you have images, you have to run a big sort of matching algorithm. It's like a combinatorial optimization algorithm. So people work on that separately. And then for the reconstruction part, we are given that as our input. So the pairing matters a lot. So if your pairing is bad, it's, normally when they're trying to reconstruct, they will throw out the bad pairs. So yeah, it's not an entirely abstract theoretical thing. It's something that has practical meaning.
Okay, thank you.
Does that answer your question?
Yeah, sure. Thank you. Now I understand.
Okay. Yeah, so mathematically we could do whatever we want, but it doesn't make sense in the physical world to do that. So yeah,
Yeah,
so
I was
pairing.
looking at it only from mathematical viewpoint.
Yeah,
That was
absolutely. Yeah, it's a very valid question, because for us mathematicians, we don't worry about that kind of thing. But
okay.
it's given to us. We cannot change it.
Okay, thank you.
But of course, I'm asking now, if you're arbitrarily allowed to make two sets of points, what sorts of constraints will you have to satisfy? Okay, so back to some history. So on the left here is the French mathematician Charles from all the work on conics, the 3,264 conics. Maybe some of you know about that. So anyway, he asked this question back in 1855. So here's a question he asked. He says, if you give me 7 point pairs, UIVI, so 7, and I know that there are images of 7 points, Q1 through Q7 in the world under 2 projective cameras, he asked whether you can show that there is at most 3 projective reconstructions up to automorphisms. Okay, so up to automorphism, there are only 3 different pairs of cameras and 3 different pairs of cameras and world points that will reconstruct this. So this was a question. It's not exactly our question, but it's a type of question related to our question. This was solved by Hesse in 1863. So these are old questions. People were interested in these questions because they liked projective geometry. These are natural questions from that world. But there's another reason why this was studied from a long time ago. So already back in the 1800s, they had photogrammetry, which is the study of making measurements and understanding 3D objects from pictures. So for example, you might have a balloon that flies in the air and takes pictures of the terrain. And then you would want to make topographic maps of the terrain. Or do you want to make measurements? It's used in archaeology. It was used in land survey. So people really wanted to understand what the 3-dimensional object looks like by just looking at pictures. So these are old questions, and our question fits in this type of question that we're asking. Okay, when can you reconstruct given some set of images? Good. All right, so with all that background, I think I'm sort of ready to tell you how we might approach this problem. So let's look at the case of 2 cameras, for instance. So here I have 2 cameras. Here is the first one. It's called A1. It has a center C1. Here is the second camera. It has center C2. And if I take a picture of this point Q in the 2 cameras, then in the first one, I have image U. And in the second one, I have image V. Okay. This orange line is special. It is a line that joins the centers of the 2 cameras. It's called the baseline of the camera pair. And you see that this orange line cuts the 2 camera planes in these 2 special points. These are called epipoles. And what E1 is it's the image of C2 in the first camera. And E2 is the image of C1 in the second camera. Okay, so these epipoles are images of the different centers in the other camera. And the first thing you notice is that if you give me Q and this U, which is the image in the first camera, I cannot put this V wherever I want, because all of these things, the Q, the U, the C1, the C2, the V, all of these things have to live on a plane, right? This picture tells you that you have to live on a plane. So if you give me U and you give me Q and you give me the 2 centers, then I have to put V over here. Okay, so that tells you that there is some strong constraint that connects the U and the V together. I cannot arbitrarily put V in the second camera. So mathematically, the way you express this planarity, so this plane is called the epipolar plane. And the way you express it is like this. I won't really explain why it's expressed like this, but it's just, it's fairly simple. So what needs to happen is there needs to be some matrix X, which is 3 by 3 and real. It has to have rank 2. And it has to connect the U and V like this. So we need to satisfy V transpose X U equal to 0. So X is unknown. It's a 3 by 3 matrix. U and V are given. So the U and V are coupled through this X by this equation. Okay. So that this satisfying this equation is exactly the same as saying that U and V lie on this plane, on the plane that's defined by Q and the baseline. All right. So this gives us a different way to to work with this constraint. So we're going to actually work in the space of these x's. So I'm going to talk about these x's for a moment. Okay, so this is called the epipolar equation, and it's a linear equation that connects the v and the u together. So v and u are known, x is unknown. All right, so this x is called the fundamental matrix of the cameras. So basically what we've done is the following. We started with the cameras. There were two cameras and there was a projective reconstruction, let's say. So these two cameras uniquely give me this x. Okay, so from A1 and A2, I can construct a fundamental matrix. And that fundamental matrix, as I said before, is rank 2. It's 3 by 3. And for every pair UI, VI I had, I need to satisfy this equation. VI transpose times x times ui must be equal to 0. So I get k of these linear equations. They're called the epipolar equations. So this is so cameras gave you fundamental matrix, and this space, these fundamental matrices in turn can also be thought in a different way. So this is a rank 2 matrix of size 3 by 3, which means it has a unique, or it has a one-dimensional right kernel and a one-dimensional left kernel, right? The null spaces on both sides are one-dimensional. So they are generated by unique points in projective space. So there are 2 points, E1 and E2, such that x times E1 is 0 and E2 times x is 0. So these are, I'm calling them E1 and E2 because they are exactly the epipoles of the cameras that we started with. So there are 3 worlds over here, and you could work in any of these worlds. You could work in the world of cameras, which is how I posed the question in the beginning, but you could just as well work in the space of fundamental matrices, which are rank 2, 3 by 3 real matrices that satisfy these equations, or you could work in the space of their right and left kernels in this epipole space. Okay, so there are 3 possible places we could work.
So,
yeah.
So Rekha, you said having a 2 cameras correspond to giving a matrix, right?
Yes. Yes.
So how does those 2 matrix fit connect with this fundamental matrix?
So the way you construct them, I can't draw, unfortunately. So the way you construct the matrix is you stack up the 2 matrices together. So A1 is a 3 by 4, A2 is a 3 by 4. So make a 6 by 4 matrix, okay? And then there's a particular way in which you take 4 by 4 minors of this matrix. So take 4 by 4 determinants, and you put them in a particular way into a 3 by 3 matrix. That's what this X is.
Okay.
So that's the formula by which you could construct the X. It's a kind of tensor that you make from stacking A1 on top of A2 and then taking 4 by 4 determinants and putting them in special places in the 9 possible places of the 3 by 3 matrix. Does that make sense?
Okay. Yeah.
Okay. But geometrically, it comes from this plane. The cameras, the baseline of the cameras and so on, it gives you this X. It connects an image here to the image there. So that's the geometry. But if you actually wanted to algebraically construct it, you go through this minor construction.
So X is determined already by A1, A2, you're saying?
Exactly, yeah. X is determined by A1, A2. So it's unique.
Yeah,
okay.
But okay, yeah, thank you, yeah.
I mean, there is a group action, but we're kind of ignoring it. So everything is only up to P3 homography, but let's forget about that. So you can multiply everything with like a general linear group of size, whatever, 4 by 4 or something like that. So there is a group action here, but if you ignore that group action, there is 2 cameras uniquely give me a fundamental matrix. From the fundamental matrix, you can uniquely reconstruct the cameras up to group action. Okay, so this is really a bijection kind of thing.
Okay, yeah. Okay.
Modulo GL4. Okay, there's a group action, but if you just mod out the group action, this is a bijection. So instead of looking at cameras, we could work in this space of matrices. Once you have the matrices, hopefully this bijection is this clear, the second bijection? All we're doing is we're taking X and passing to its right kernel and left kernel, which is unique because I have a rank 2 3 by 3 matrix.
Correct.
So it has a unique, it has a one-dimensional right kernel and a one-dimensional left kernel, which projectively give you two unique points, E1 and E2. Right, so the one-dimensional kernel is generated by one point if I think of it as a projective point. That's what the E1 and E2 are. And those two happen to be epipoles of the cameras. So these three worlds are all connected together. Is that clear?
Yeah.
Okay.
Thanks. Yeah.
No worries. Okay. So I'm going to think of, again, if you like projective space, you should think of the space of 3x3 matrices as P8, because I can take my 3x3 matrix and I can just concatenate the rows together. So I will get a 9-dimensional vector if I just unravel the matrix into a long vector. But if I have a 9-dimensional vector in affine space, that's a point in P8. Okay, so we think of the space of 3x3 matrices as P8, and we think of the space of epipoles as P2 cross P2. Okay, so if you like algebraic geometry, you can think of these two things are happening in P8 and P2 cross P2. Otherwise, you can just think of it in terms of linear algebra like this. Okay. So these are the three worlds that we can work in. So now what we need to do is impose chirality, right? So when I impose chirality, in the camera world, we had all those inequalities in terms of principal rays. You can translate that into the two different worlds. So if you translate that into the world of matrices, you have these inequalities before become certain polynomial inequalities. So I'll write them as gi, gj, grade A equal to 0. So each gi and each gj is a cubic polynomial. So the product is a degree 6 polynomial. So I get a whole bunch of polynomials. There's one for every pair I and j between 1 and k. So they're high degree polynomials, and you need to satisfy these polynomial inequalities. So the x's that we want need to satisfy these inequalities. And if you transfer that check into the other space, then it's sort of a combinatorial check. So if you know oriented matroids, what you end up checking is some sort of determinants and their signs and so on. Again, it doesn't matter exactly what it is, but this is actually the more interesting thing, that you end up needing x's that satisfy certain polynomial inequalities. Okay. So we're not looking at algebraic varieties. We're actually looking at things that need to satisfy inequalities. So it's a little bit more complicated. Right. So now let me just translate all of this into geometry, because that's kind of where the action is. So if you think about what a fundamental matrix was, let's just translate what that meant. So it was a 3x3 matrix that had rank 2, and it needed to satisfy some equations, those epipolar equations. So let's start with the rank 2 part. So I'm going to just let R2 be all the 3x3 matrices that have rank at most 2. That means they need to satisfy the equation that their determinant is 0. Okay, so this is a single algebraic equation that says the determinant of a 3x3 matrix is 0. It's a hypersurface, so it's a single equation in P8. And it has degree 3, which just says that the degree of this polynomial is 3. This is a 3x3 matrix, so when I take the determinant, I get a degree 3 polynomial. So this is some surface that lives in P8. And then I need to cut that surface with all these equations, right? I need X to also satisfy these equations, these epipolar equations. So this is a subspace. I'm going to call this LP. I'm going to call subspaces planes, but plane doesn't mean two-dimensional. It just means it's a subspace. So I have a subspace, and I need to intersect these two together. So I need to take the plane, and I need to cut it with this determinant X0 equation. So altogether, I get some algebraic variety, which is the common intersection of R2 and LP. But the fundamental matrices are not exactly this intersection. They are the real things that live in here. So these blue things, you can put it in complex space. It's actually better to put it in complex in C to the 8. But inside that, I really want to only care about the real part, and I only care about the rank 2 part. So I don't, if there's a rank 1 matrix in here, it's not interesting. It's not a fundamental matrix. So we don't care. But so you need these additional conditions to actually make it a fundamental matrix. Okay, so this is the space from which these fundamental matrices arise. All right, so that's a little bit of algebraic geometry. And the second piece we need is what I'm going to call walls and corners. Okay, so this is linear algebra. So what we're going to do is we're going to take this point ui, and I'm going to look at all the 3x3 matrices that has ui as its right kernel. Okay, so this is a bunch of matrices, and I'm going to cut it with my subspace LP, this epipolar equations. So this I'm going to call a wall. I'm going to call it a UI wall. It's a subspace altogether because this is linear, so this is a subspace. Similarly, you can make a wall for the VJ point. You look at all the x's that have VJ in its left kernel, you intersect with LP. These are both subspaces in P8, and they have codimension k plus 2, meaning that they have k plus 2 independent equations among them. Okay, so this is just linear algebra. And these we'll call walls. And sometimes, or oftentimes, we want to intersect them. So we want to take a UI wall and intersect it with a VJ wall. So this is a smaller subspace. And this I'm going to call a corner. So we're going to call this a UI VJ corner. Okay, so it has one more codimension, meaning it's one more independent equation that you need to impose. So we have these walls and corners. So here's a picture. So for example, here is maybe the UI wall, and here is the VI wall. And to be truly a fundamental matrix, you have to be either in the corner or you have to be not on any of the walls. So the condition is even more complicated than the condition I showed you before. So not only does your matrix have to be rank 2, 3x3, satisfying all these equations, it also has to satisfy this picture with respect to corners and walls. But this part is not very important for this talk, so I'm just going to gloss over it. But the walls and corners are actually important. So that'll come back. Good. So let's do a small example because I've already introduced several things just to see what all this looks like. So let's come to the case of 5 point pairs. So I have 5 U points and I have 5 V points. Okay. So in that case, I have 5 equations, right? The epipolar equations, there are 5 of them. And if you have 5 equations in P8, then the subspace that you're looking at is isomorphic to P3, right? If I cut with 5 equations in P8, I'm down to something that looks like P3. So this LP is a P3. And when I cut it with R2, which is just determinant x equal to 0, what we get is a cubic surface inside this P3, right? Because I'm cutting the subspace with this degree 3 hypersurface. So you get a picture like this. So this is a picture of a cubic surface. We saw it before. And this is how this space of fundamental matrices looks like. Okay, it's this cubic surface, but it's not everything here. I only want the real part and I only want the rank 2 part. So it's a little bit more complicated, but this is the ambient surface that it lives on. And these walls that you saw, the UI walls and the VJ walls, they're lines on the surface. So that's why we call them walls. They're 1 dimension lower than the surface. So you get 10 real lines because I had 10 U points and 10 V points. Okay, sorry, I had 5 U points and 5 V points. So altogether, I get 10 lines from my input. And this particular surface, you will see, has 27 real lines. We will see that everything we do from vision will end up giving you a cubic surface with 27 real lines. 10 of them come like this, okay, from the input. And then on the surface, I also want to satisfy those inequalities, the GIGJ. They're very hard to look at or understand. But what you can understand is that they become 0 exactly on the walls. So GI and GJ are 0 exactly when you lie on the I wall or the J wall, okay? So even though it's hard to see where the region is, you can understand where the sign is going to change. The sign is going to change exactly on these walls. So the region we're looking for is some region on this cubic surface that is bounded by lines and has some more restrictions on it, okay? Right. So that's an example for k equals 5. So if you want a chiral reconstruction, you want the chiral region to be non-empty. So that's mathematically where we are. Okay, so there's some complicated semi-algebraic region that has to be non-empty for a chiral reconstruction to exist. And you'll see it's very subtle. So here's an example. So here I took 5 points. They're exactly placed. This is not an arbitrary picture. So I've exactly placed 5 points in some place. And then, so this is one image. And then on the other side, in the other plane, if I took these 5 points, I will get a chiral reconstruction. But if I modify this slightly, if I take this 0.5 and I move it to the other side, like here, I no longer have a chiral reconstruction. Okay. So it's not easy to see why this is true. So I'll try to explain why we know this is true in a moment. Okay. So this is an example of 2 sets of images, U and V. This is one pair. Here's another pair. One has a chiral reconstruction. The other one doesn't. Okay. So what are the results? What can we prove? So like I said, what we were after was to find out where the threshold is. When can you always say there's a reconstruction, and when do things start to break down? So the first result is that if you only have 3 points on both sides, if k is at most 3, then unconditionally there's a chiral reconstruction. It doesn't matter how you put the 3 points on both sides. Okay. So up to k equals 3, everything is fine. There's no geometric condition. If k is greater or equal to 5, then you may fail to have a chiral reconstruction, like we just saw in the previous slide. And this can happen even if the u points and v points are in general position. So they don't have to be in any highly non-generic place. Even if they are in general position, this can fail. So K5 and onwards is not guaranteed. K3 and below is unconditionally fine. So what's interesting is what happens in 4. Okay, so let's see what happens in 4. So if you have 4 points on both sides, then things are quite a bit more intricate. So if you think just in terms of combinatorics, what can happen is on one side, you may have the 4 points in general position, which I wrote in the square. So general position just means that 3 things don't lie in a line. Okay. So I could have both sides, things are in general position, or I can have one side is in general position, in the other side, 3 points are on a line, or I can have 3 in a line, 3 in a line, or I can have 4 in a line, 4 in a line, and so on, right? There are 6 possibilities for 4-point pairs up to combinatorial type, okay? And the result is that in the first 4 types, this type, this type, this type, and that type, A, B, C, D, there is unconditionally a chiral reconstruction. But in the 2 bottom types, these 2, you may fail. You may succeed, but you may fail as well. And so that's the theorem. So this result is complete in the sense that it's not up to genericity or anything like that. It's just a complete result. And you can write the result in terms of ranks of these points. So if you take the points and write them as the columns of a matrix, then the result is that if the rank of one side is the same as the rank of the other side, then there is a chiral reconstruction. And in the other cases, you may fail. Okay. So this answers the question completely that I asked in the beginning, because we've sort of figured out what happens for every value of k. So k equals 4 is intricate and interesting. K less or equal to 3 is completely fine. K above 5, you will fail even in general position. You can fail. So in some sense, with positive probability, you will fail, right? It's not like there are some isolated examples with positive probability you can fail in k greater equal to 5. Okay, so those are the main results. And then to finish the talk, I want to talk a little bit more about k equals 5, because that is the most interesting case, and we already saw a bit about it. So this is where these classical cubic surfaces come up. So we already saw that when you have k equals 5, the epipolar variety is this cubic surface, right? We have this R2 intersect LP. Now I'm going to assume generic, okay? So if I assume generic points, then the surface is not only cubic, it's actually smooth and irreducible. So smooth just means, there are no singularities. Irreducible means it has only one piece. It doesn't break into pieces. So it's just one piece, exactly like you see here. And this cubic surface, so all smooth or all non-singular cubic surfaces, they can be represented as it's a determinantal surface. They have a determinantal representation. You can write it as the determinant of something equal to 0. And in our case, it's really easy to see why, because the subspace LP that we had, it was a subspace, so it has a basis. So let's pick the basis. So if I pick the basis, the subspace has dimension 4 as an affine subspace. So I pick a basis, say M0, M1, M2, M3. And then anything that lives in the subspace is a linear combination of things in the basis. So it looks like M0, Z0 plus M1, Z1 up to M3, Z3. And then if I wanted to also lie on R2, I want the determinant of that to be 0. So I can get a representation of this surface as a determinant naturally from the input that we had, okay? So this is a general fact that such a representation exists, but in our case, there's an explicit one. And now we can see the 27 lines. So let me show you all 27 lines that live on this surface. So the first 10 we already saw, they came from the U walls and the V walls, right? Because there were 5 U's, 5 V's. So I got 10 points, 10 lines, sorry. Now it turns out these 10 lines secretly carry 2 more lines. And the way they carry the 2 more lines is like this. So take your input and make them into matrices. So look at V1 times U1 transpose. This is a 3 by 3 matrix, right? Because V1 is a 3-dimensional column vector. U1 is a 3-dimensional row vector, so U1 transpose. So when I multiply the two together, I get a 3 by 3 matrix. So this is a 3 by 3 matrix, and make all 5 of them. V1, U1 transpose up to V5, U5 transpose, okay? So if I look at the span of these matrices, there are 5 of them. They will span in projective space something 4-dimensional. And this 4-dimensional space will cut the rank 1 matrices. The rank 1 matrices also form an algebraic variety. It has degree 6, meaning, so if you cut the rank 1 variety with the space, with this span, it'll cut in 1 more rank 1 point, right? Because generically it'll cut in 6 points. And so there is another rank 1 matrix that lies in the intersection that gives me a U0 and a V0. And if I form those walls, I will get 2 more lines. So I'll get 12 lines like this. So I have 6 lines that are coming from the U's, because I'm also including U0 now. So these are the 6 lines from the U's, and I have 6 lines from the V's, okay? And they form what's called a Schläfli double 6 on this cubic surface. So this is a very, very special configuration of 6 lines. So I have 6 lines on one side, 6 lines on the other side. And the definition of a Schläfli double 6 is that if you look at lines in one side, they do not cut each other. So they are all pairwise disjoint. Same for the other side, they're all pairwise disjoint. But if you look at a UI line on one side and a VJ line on the other side, then they intersect if and only if I is not J, okay? So it's a very, very special intersection pattern. You have 6 skew lines, 6 skew lines, and the only way they intersect is if you take an I line and a J line where I and J are different, okay? And that is the definition of a Schläfli double 6. And every time you have a set of lines like this, you will get a unique cubic surface that they live on. And in our case, it comes naturally from these cameras. Okay, so that's a very nice one. And then there are 15 more lines that are real. And they come from these U's and V's, because what you do is you take the U line, a UI line, and a VJ line, look at the plane they span, and that'll be tangential to this cubic surface. And that tangential plane will cut the surface in 1 more line. And therefore you get 15 more lines. Anyway, that part is not so important, but they're all real. That's the important part. So if you know cubic surfaces, you know that there are different types of cubic surfaces. There are ones with 27 real lines, 15 real lines, 7 real lines, and then 2 types that have 3 real lines. So ours is this very special first type, and it always comes from everything that the cameras give is of this type. Okay. Right. So let's see, where are we? Okay. So I only have a few minutes left. So let me just try to explain.
Rekha, I
Yeah.
think this 27 lines has connections with designs, 45 to L3.
Oh, I don't know. Maybe. What kind of designs?
Symmetric designs.
Oh, design. Yeah,
Okay.
maybe. I don't know. Yeah,
Okay.
that's a good question. It could be. Yeah, they are. Yeah, I don't know if they have a connection to designs. Yeah, we were actually surprised to see this, that these surfaces end up with these 27 real lines.
Sorry, I missed something. Maybe this Leifly is a person who.
Yes,
and
Schliffli is a
Zecharius
person.
have written a paper.
Yeah, so he was a Swiss mathematician who worked on these cubic surfaces. I don't know exactly when he lived. So most of the early, the fact that there are 27 lines is due to Salmon and Cayley. It was a question asked by Cayley in the mid 1800s, answered by Salmon, George Salmon. And then Schliffli is also, I don't remember exactly when he lived. So it was either late 1800s or 1900s, maybe. He's a Swiss mathematician, and he defined these double six lines.
Okay.
And there's a lot of the cubic surface literature is quite classical. So there's a book by Segre, for instance, that has a lot of combinatorics of cubic surfaces. It's very old stuff.
Thanks.
Yeah, it's very beautiful. There's a lot of combinatorics in it and other things. Yeah, Schliffli was a Swiss mathematician. Good. Other questions?
I think Sanjeevani was mentioning something. I forgot.
Yeah, this 27 lines on a cubic surface. There's a paper by Arens and Zecharius where they have shown that this is a strongly regular graph with the parameters 45 to L3.
Oh, cool. Okay. Yeah, there's lot of nice things about these things, these surfaces and their lines. And this is only one type, and then there's 4 more. So thank you. So how much time do I have left, Vijayalakshmi? We're almost done, right?
Yeah, I think the time is, yeah.
We
Okay.
started a bit late, so maybe 6 more minutes, Rekha.
Okay, so yeah, I only have a couple more slides left, but I can also cut them if needed.
Oh no, it's
So
okay.
anyway, let me. I'll just do a couple more slides so you can see the P2 cross P2 as well. So the last thing I want to show you is how we can look at all the same things in P2 cross P2, which was the space of the epipoles, right? So the way you map to P2 cross P2 is you start with your X, remember it was rank 2, and you just map X to its right kernel element and to its left kernel element. That's the map, okay? So just map it down to the right and left kernel. So we go to P2 cross P2. And algebraically, you can do this through the adjoint matrix. So the adjoint matrix is, like it's the cofactor matrix of X, but transposed. So anyway, details are not important, but this is what you do, map to the right and left kernel. So if you do that, then this is what happens. So the cubic surface will map down to one P2 and then the other P2, okay? So let me just explain one side. So if you map to the left, all the U lines will map to the U points that we had in the beginning. So there are 6 U lines, they will map to these 6 U points. And the V lines will map to conics. And the way they map to a conic is, if you take the line V1, it'll map to the conic that goes through all the U points except U1, okay? So the conics are missing one point at a time. So the lines, that's what happens if you blow down. This is a blow down to the left. And similarly, if you do to the right, you will see that all the V lines go to the V points. There are 6 of them. And all the U lines go to conics. Okay, so this is what happens. So now you can see what's happening in the 2 P2s. And once you can see this, you can actually see the chiral region. So the chiral region upstairs was in P3. We can't really see it. It's bounded by these lines. But once you map it down, you see that they are going to be bounded by these conics, because the conics were the lines upstairs, right? So now you can see this gray region and this gray region. So that's where the epipoles have to lie for there to be a chiral reconstruction. So if there is no gray region in the pictures that you get, then there is no chiral reconstruction. Otherwise, you can see the regions in the 2p2s. So that's basically the geometry of what's happening. And then we write down a test that says you don't really need to construct the region. You just need to test the 20 corners in the Schläfli double six. So you make a little test on each one of those corners. And if that it passes the test, then you're good. Okay. So it's sort of, this is the picture in the 2p2s. So I think this might be a good place to stop. I had a few more slides for the more algebraic geometry people, but I think we can stop. So I think that's a good place to end the story. So thank you.
Okay, so we thank Rekha. So we are open to questions now. So do people have questions?
May I ask a question? I'm Indranath.
Yes,
Yeah,
please.
Okay, so the question is in Chesel's original question, which you said is part of the historical development. That there also he asked about there are at most 3 projective reconstructions up to P3 automorphisms.
That's
so,
right.
So how do you address that issue in your formulation of the problem?
Oh, so when you so the thing is, yeah, this I kind of pushed it under the rug. So the point is that if suppose you're able to reconstruct 2 cameras and some world points. So let's call them A1, A2, and then you have Q1 through QK. Okay. Now what you can do is so remember the cameras are 3x4 matrices, right? So you can multiply on the left of each camera with some 4x4 matrix. So let's call it H. So I can do A1 times H inverse and A2 times H inverse. That gives me 2 other cameras. And to make the equations work out, what we do is we multiply all the Q points with H. So if before we had A times Q is equal to the image. So now I will have A times H inverse times H times Q is equal to the image, right? Because the H inverse and the H will cancel out. So there is an entire GL4 orbit once you have one reconstruction. So that is what he meant by the P3 automorphism. Does that
and
make sense?
that doesn't disturb your this constraints based on those semi-algebraic sets. I mean those.
So so for the semi-algebraic sets, it's a good question. Let me think for a moment. I'm not exactly sure. So we would. No, it can disturb. It can disturb. So what can happen is that, it's a little bit tricky. So if you have a reconstruction, it's only sometimes that you can push it with a homography into the chiral region. So we understand that. And there's actually a theorem that tells you when you can find something in the orbit that will lie in the chiral region. There has to be a condition that is in terms of the principal rays. So it's not always true that if you have one thing in the orbit that is chiral, everything is chiral. That's not true. And there may be nothing in the orbit that's chiral. Does that answer your question?
Yeah, sure. Thank you so much. Thank you so much. Yeah.
Yeah, and please feel free to turn on your video too, so
Yeah.
I can see you. I'm just looking at a blank screen.
Yeah.
So
Can I ask something, Rekha?
yes, please go ahead.
The result that you said was that if you had more than 5 points on in the UIs and the VJs, then it's almost the probability is very high that you will fail to get a reconstruction.
That's not exactly the statement. So let me say this a little bit better. So what we showed, so sometimes there can be a chiral reconstruction. So for example, if this really was the picture from two, if they were real pictures, obviously there's a chiral reconstruction, right? So it's not true that they always fail. But what we showed is that there are things in general position that fail, right? The pictures I showed you, there's some blue points, some green points. They're in general position and they fail. So if you wiggle them slightly, they will still fail, because the condition for testing is a sign condition. And the reason we know that they fail is because the sign is strictly positive. Okay.
Right.
So if you wiggle those points slightly, they will still fail. So there is like a whole dense region in the space of 5-point pairs where they will fail. So it's in algebraic geometry language, it's Zariski dense. So there's positive probability with which it can fail. They're not like isolated, non-generic instances.
So I wanted to ask if there are further conditions that you could put on the positions of these points, which would then ensure that they are reconstructions. Is that possible?
So it's exactly those GI-GJ conditions.
Okay.
Right? So if you satisfy those GI-GJ greater equal to 0, then you will definitely be able to reconstruct. So what we're doing is finding point pairs for which these GI-GJ regions are empty.
Right.
Yeah. So in some sense, we have the complete description. The question is but the trouble is that when you look at them first, they're very, very complicated. It's not really clear how to test for this or find these regions or, whatever. They're semi-algebraic conditions, right? Typically, they're very hard to know if those regions exist. But the test that we devise, which really works in those P2 cross P2 pictures with the conics and so on, it just ends up testing the 20 corners. So, yeah.
So are there any further questions?
I think there's some questions in chat.
Yeah.
Manoj Raval. So question is, Rekha, can you read it or something?
Yes, I can read it, but I'm not sure I understand it. So please explain.
Yeah, please explain.
Manoj, are you here?
Yeah. Hello?
Yes.
Hello, good afternoon, everyone.
Yeah, please go ahead.
Ma'am, I just want to ask, since we are talking about image and all, that can we say, does it make mathematical sense that our image, the image we capture is nothing but a homomorphic copy? And if there is any identical twin of us, and that is going to be an isomorphic copy. So does it make mathematical sense?
Yeah, it does. It's a sensible question. So basically there are many ways to describe how the two images are related to each other. And one way to describe it is that if you look at the epipole in a camera and you look at all the lines that join the epipole to U1, U2, U3, and so on, and you also look at the epipole in the other camera and look at the lines that joins it to V1, V2, V3, and so on, there must be a homography between the two. So that's another condition for them to be images. So there must be a homography that sends these lines to those lines. Right. So in that sense, it's a kind of isomorphism. Yeah. So that there's strong conditions actually, because you can't put images wherever you want, unless you have 3 points, then you can do whatever.
Yes, ma'am. And what about if we have our identical twin? So can we call isomorphic copy?
I'm not sure what you mean. What do you mean by identical twin?
The same copy of us. Suppose.
Oh, I see. Yes, two pictures that are exactly the same.
Yes, ma'am.
I would think that's okay. Yeah, if it's exactly the same 2 points.
Thank you, ma'am.
Yeah, I need to think about it, but I think that's okay. All right.
Can I ask one more question?
Yes, please.
Yeah, you said that that chiral representation is not there if you wriggle it slightly. Then also it's not there. But what about those which is there? Like you have these two images and you move it slightly.
Yeah,
You would still get chiral
yeah,
representation.
you will. You
So
will.
then it's not exactly same. I mean, you have to wriggle both of them, but if you wriggle one of them, then would you fail or not fail?
You probably won't fail. Usually these things, because we're testing for the sign test is a strict test. You're testing for strict positivity with the sign test. You will get dense regions around your 5-point pairs for which it'll be fine. So if you look at the space of 5-point pairs, you will get regions where things are fine and regions where things are not fine.
Okay.
That's the geometry, I think, of what's happening.
So one more question. When you say positive probability, which measure are you using?
Oh, all I mean is that it's not a zero, it's not a measure zero set, right? Under whatever Euclidean topology you want to put on it.
Because Jarsky density could be also for discrete subsets, right? So
Yeah.
just
Right. These are semi-algebraic sets, so they are not filling the whole space. But all I'm trying to say is that it has an interior, right? So when you take when you take all the equations that vanish on it, I mean, when you take its Zariski closure, you'll just get everything because it has an interior.
Oh, okay. So it has an interior is important because even
it's important. Yeah, exactly.
Subset could be Jarsky dense. So.
Yeah. So it's not like a line or something, right? It's not like a curve. It really has an interior. So when you take its closure in Zariski topology, you'll end up getting everything.
So you are saying chiral and non-chiral both can be dense set?
Yeah, they're semi-algebraic, right? So they are like sort of, they're not algebraic varieties. So they are regions that are bounded by polynomials.
Okay.
So they can both have interiors.
Okay.
That makes sense?
But yeah, it's a bit strange for me, yeah.
Yeah, they're semi-algebraic, which is really complicated compared to working with equations.
Okay.
But especially to test them is difficult.
Can I ask one question? So this difference that you got for 3, 4, 5, is it because of the size of the matrix? I mean, why, like for k less than equal to 3, you always have at 4 some behavior? I mean, does it have to, like if you go in higher dimensions, you would see because of the size of the matrix? Or?
No, it's just the size of the variety. So for example, so in the case of k equals 5, what we ended up was looking on this cubic surface. We needed certain regions to exist. And there we fail, okay? But when you look at the k equals 4 case, the variety becomes a 3-dimensional object instead of a surface. And it still has walls and so on, but it's a fatter, bigger object. And when you look to k equals 3, it's a 4-dimensional object. So it just has more real estate. So it always has some region that's going to be chiral. It's just the geometry. And you don't need to study beyond k equals 5, because once you have a bad example in k equals 5, it'll continue to be bad even if you add more points, because if some piece of your image cannot be reconstructed, then the whole thing cannot be reconstructed. So k equals 5 is where the analysis stops as soon as you find. So these are these threshold kind of answers that people like in vision.
So my question is also like, if you, I mean, now you were working with like P2 and P3. So for example, if you work with PN and PM and like that, I mean, you can still talk about those, I would suspect, right?
Yeah,
you can talk about all those questions.
You can certainly ask the mathematical question. It's just that it doesn't have physical meaning.
Sure. Right.
So I do have an engineer as my collaborator. So we are not allowed to ask abstract mathematical questions that don't have physical meaning. But I'm joking. But there are people who have studied some parts of these questions in more generality. Like you can just, as a mathematician, you can ask those questions, right? What happens if you do this from PK to PL or whatever? And there are some interesting answers for several vision questions, but we are
I asked something from the answer you just gave, which is, you said your engineer collaborator refuses to let you take on. So how exactly does what you have found have, use in the real world vision reconstruction?
Yeah, it's a very good question. So it's not like I don't know if Samir's here, so I should be careful. It's not like he doesn't want us to take on the question. It's just that we feel like it's most useful to study the actual question. If you want to extend it, you can. What does it do in real for actual practical application? Probably nothing at this point, because these are just very foundational math questions that are often not studied by engineers, right? Because they don't really care. Like when you're trying to reconstruct, you never actually get a true reconstruction. So in reality, everything is noisy. So if you see pictures, like if you have satellite pictures of something, it's noisy. So then you're not trying to reconstruct the actual image. You're just trying to make the maximum likelihood estimate, right? So you run some optimization algorithm and you say, okay, let's get as close as we can in some kind of metric. So in some kind of distance, you try to get as close as you can. So it's never really the correct thing, but it's good enough. And we cannot make out, like the eye cannot see it. So that's good. So that's the other end of the spectrum, when you just really do it with numerical algorithms, and it's very much an engineering job. So we are on the other extreme, where we're asking these very simple math questions in some sense, which in a way is surprising that the answers people haven't worked on it on these very basic questions. People have worked on it, but they're still open questions.
So are there more questions?
There is one more question. There's one question.
May I ask a question?
Yes, please.
Yeah, I have already written it in the chat box.
Oh, why is the camera 3x4?
Why is this matrix?
Right, so that is only in the case of these projective cameras that I told you about. So in the case of projective cameras, that is what they are. They generalize the pinhole camera. If you think about what the pinhole camera is, it exactly ends up being a 3x4 matrix. But in real life, the camera map does not have to be linear. So my matrices my maps or cameras are linear maps from P3 to P2. That's the kind that I talked about. But you could have, for instance, usually you have lens distortion, right? Like if you have a fisheye lens or something, there's a distortion. And then the map takes Q to a rational function. So you may end up with some more complicated polynomial rational functions as the image. Okay. And you can ask the same question again, like when is it chiral and all that kind of stuff, but it's all unknown. So it can be studied. The more complicated your camera model is, the more complicated the answer is going to be.
Yeah, my question had that basically I was working on depth recovery in a few problems, and that is why I asked you, because there we did not take this 3x4 matrix. It was
that's right.
Complicated matrix, and I understand now, as you said, because it's not a projective camera which we were looking at.
Yeah, and even a regular calibrated camera like we have in our digital cameras, where we know the calibration, it is not just a 3x4 matrix. So it's a 3x4 matrix where the first 3x3 part is supposed to be a rotation matrix.
Yes.
And the second one is an arbitrary vector. So that already imposes extra conditions on your camera. So that's maybe the next level of complication, but it can even be a nonlinear map, right? Which is much more complicated than what I presented.
Yes.
And then all of these questions, projective reconstruction, chiral reconstruction, all of them can be asked for all of these models. And it's a new math question.
Okay.
And with maybe more complicated answers.
Yeah. Okay, thank you.
So Yeah, there is some comment on the chat box. Rekha, can you see it?
Yes, yes. Article, yes, I can send a link. That is fine. Do you consider projective representations? So I didn't quite understand the last question. Groups.
Professor Ajit Iqbal can speak herself. Hello?
Yes, please.
Hello. Yeah, you see there, when you take two elements of the group, G1 and G2, then the representation pi G1, G2 is alpha pi G1 into pi G2, where alpha is a number. So such representations are called projective representations. They were called fractional representations by Schur about 100 years ago, and 3 papers he has on fractional representations. So since you are considering projective spaces, I thought I would mention or ask or whatever you may call it.
Yes, yeah, thanks, but I'm not sure I know what the connection is. So yeah, but yeah, so these are the setting I know about.
You see, when you take a vector and you multiply it by scalar and it is same in your eyes, then when you take a matrix and multiply it by a number, then image will be same. So the product of two represented matrices is not necessarily the representation of the product. It could be a scalar multiple also.
I see. Okay. All right. Yeah, thank you.
Rekha, if let me ask a stupid question. So my understanding that you are constructing 3D images out of 2D objects like that. So
right.
Suppose if you have more than 2 cameras,
you can do the same.
You can do the same, and
yeah.
I think the outcome will be better if you get a result, right?
Right. So in the case of projective cameras, we understand what, I mean, in all cases, we understand what needs to get done. It's just that the semi-algebraic sets you're looking at are getting more and more complicated. So there is, mathematically, you can write down what needs to happen in all of these cases.
So it has more constraint then, right?
It has more constraints, exactly.
So it may sooner, in fact, your chiral reconstruction kind of stuff.
Yeah, it's so even if you just think of projective reconstructions, right? So what I said with 2 cameras is you need to satisfy these epipolar equations.
Yeah.
If you have 3 cameras, you need to satisfy a degree 3 equation as well. It comes from a tensor called the trifocal tensor that connects 3 cameras together. And then so there are these degree 2 equations, degree 3 equations, and then there's a theorem that tells you that you don't need anything more, like you don't really need degree 4 and 5 and so on. So you can construct an algebraic variety, it's called the multiview variety, that will be cut out by all of these equations. And then on top of that, we need to impose chirality, if you want chiral. And people haven't really studied, I mean, we have a paper that generalized chirality to multiple cameras, but we haven't made this sort of detailed study of it.
Okay.
Yeah, so there's theory, but the question is if we can say something more special, right? Like these cubic surfaces with lines and so on. We don't have like very detailed results.
Okay, but there are people looking at this such thing.
Well, I think these kinds of theoretical questions, probably the very math-oriented people are asking.
So is it just a theoretical question, or do you think it has some kind of application, real life application, those kind of things?
Chirality, I don't know. So my sense is that this is a math question, I think, that, I'm not sure it will do a lot in terms of actual practice, because in actual practice, like I said, they often don't have actual images. It's always noisy. So knowing whether something can be reconstructed or not is not good enough. You always want to reconstruct something approximately, right? So you want to do some kind of maximum likelihood estimate and get the scene that looks more or less like what it might have been. So this is not an exact question. This is not something we can solve for. This is like a distance question. Does that make sense, what I'm trying to say?
Mm-hmm.
Yeah,
Somewhat, yeah.
Because we want to actually reconstruct something even approximately, right? We don't want to just say, oh, it has no reconstruction, so we're done.
Right, yeah.
Right, so that's like in your, for example, when we reconstruct, like when you stitch panoramas together, when you take a panoramic picture, right? It's doing something that approximately reconstructs for you what's happening. So it's not, we still want to get something. We can't just say it doesn't exist. So then it's an optimization problem, like a statistical estimation problem. Which can be done.
Somebody is, Neela is saying something. Neela, yeah. Neela, your mic is mute.
I've muted her. It's okay.
Neela.
Yeah. So there is some question from Kapil in YouTube. So let me read that out. For curves, one has some heuristic that I does not see beyond the second derivative, which are used to justify working with cubic splines. Is there something similar in higher dimensions to justify working with cubic surfaces rather than higher degree surfaces?
Oh, so in this case, the cubic surface just comes naturally. So I'm not sure we didn't choose it. It came to us, right? Because it comes from the 5 point pairs. So I think you'd have to ask a different question to use a higher degree surface. I mean, we don't mind using any degree surface, but in this particular example, this is the natural one, I think.
It is.
But certainly there are higher degree varieties, and I mean, there are more complicated varieties in vision, and many varieties that we don't understand.
Thank you.
Okay.
So Sachi, Neela, are there further questions on YouTube?
No.
I just want to ask one last question, sorry. So how do you, you could have a 4-dimensional, not exactly image, but suppose it's a video in time, then that would be the 4th dimension, right? So do you also do something about that, or?
No, I've never worked on video. It's only valid, and it's a huge field. Vision is a really, really expansive field with all sorts of things, right? These kinds of questions that we looked at are very geometric. They are in an area called multiview geometry, which lives inside vision. But it's a massive field with all these recognition things, and like face recognition, handwriting recognition, video, all sorts of self-driving cars. I have 2 students who work on self-driving cars now, who worked on vision before. So it's a massive field, I think, compared to. So yeah, we're in there's a very particular question, but somewhat foundational in that's.
Thank you.
Okay,
so Kapil has another comment.
Yeah.
Perhaps looking for a parametric form forces us to look at unirational varieties.
Yes.
So that is his comment after your response.
I see. Yeah, certainly. So there's a lot of, and there are many other questions for which we don't actually understand the variety. We know how to theoretically say what the variety is, but we don't really know what their generators are or anything like that. So in vision, there are a lot of problems that come to you parametrized. The variety is parametrized, but we don't really know what the equations are. And that's really interesting and difficult in some cases.
So
there's a question in chat again.
There is a question. Rekha, can you see a question in the chat box?
About 4-dimensional space surfaces? No, not that I know of.
Okay.
Yeah, but there's a lot of people who work on visualization, so that could be something.
So are there any more questions? So if there aren't any, then
No,
yeah, somebody
so this
saying.
is Sundari here.
Hi.
I mean, I'm a little curious. I mean, this is out of curiosity, and I don't even know whether it is just going to have, any connection at all. See, I mean, you have this medical imaging, and so some bit of it actually comes from harmonic analysis.
Yes.
Correct.
Yes. Yes.
So this particular aspect that you have, I mean, that the kind of thing that you have, the medical imaging thing, it is the images that you take, it is not full picture of it that is going to come. Okay, it is an approximation, and so
Right.
always a possibility that the person who is assessing it, the person who is really understanding it, can make a mistake, and so the points exactly where he has to look at may not be the one which he is looking at.
Right.
So is there this particular thing, whatever you are looking at, does it improve it in any way? I mean, because it is going to be really useful.
I don't know. I mean, yeah, it's a good question. I mean, most of that, I'm not exactly sure how people do that sort of stuff. It's there's certainly some ways to do this, as you said, with analysis, right? With PDEs and inverse problems and so on. I don't know. I'm not sure whether it'll help.
Maybe in the ideal mathematical situation, we take the, suppose say I'm looking at an n-dimensional object, and I take only the n-1 dimensional images of it.
Right.
And
right.
Try to reconstruct it.
Right.
So, but then you cannot really possibly do that in an infinite number of images cannot be possible. So they take in the optimal sense some number of images.
Yeah, and that is very true. So all these reconstructions are done on points. So you take some huge point cloud and you try to reconstruct it. And again, I think the question you're asking again falls into some sort of estimation problem, right? It's because you want because the images are noisy, you want to reconstruct something that looks approximately correct. So this is a sort of statistical estimation.
Can be really better. What I'm asking is, can the approximation be better? Whatever I have got now, can the way that you're looking at?
I think not by the methods that I spoke about, because this is more about yes or no kind of question. But if you're allowed to use optimization techniques and so on, which we have in the past for other things, then yes, you can look for the best approximate solution under some metric, right? So typically what happens is that the true model is let's say some algebraic variety or a surface or something. And what you observe is off the variety, right? It's outside the variety. So what you would like to do, for instance, if your noise model is Gaussian, then what you're trying to do is to find the closest point to the variety to your observation. So closest in, say, Euclidean distance. So this is an optimization problem. It's like minimize distance from my point to the variety subject to the equations of the variety. This is an optimization problem, and people can do this, but to some accuracy. But yeah, it's a very important question, because at least from my understanding of people like neurosurgeons who look at pictures, it's very difficult. Like I have a cousin who's a neurosurgeon, and he tells me that is the most difficult part of his job, more than the surgery, to actually understand the images.
Yeah, where exactly is the problem?
Yeah,
so because any slightest, even an epsilon distance difference is always going to change the life.
That's right. And so I think just improving the quality of those images or understanding what the images are saying is very complicated. I totally agree.
Yeah.
Okay, so I guess.
Okay.
Yeah, there is
question.
No, there's a comment by, I think, Professor Ajit Iqbal.
Okay.
Yes, that's right. Donahoe has worked on this. Yes. Mhm.
So is she talking?
I don't think so.
I think it's just a chat question, right? Yeah. Oh, it's a comment.
Okay. So is there any comment on her comment?
Oh, on this comment. Yeah, I agree. Donahoe's work is great. Okay, that's good to look at. Yeah, he does a lot of stuff with medical imaging.
I think so. Donoho got this Gauss medal in 2018 ICM. You were there,
That's
Rekha,
right.
no? So
Yeah, that's right. That's
yeah,
right.
it was very impressive that something like L1 norm is used in his work to get this MRI technique to be much shorter.
That's
And
right.
it wasn't under clinical trial that time, so it would help to do MRI for children too, which is very difficult otherwise.
Yeah, absolutely. Yeah, that is very much an
Yeah.
estimation problem.
Ajit is mentioning some article in Math Student, which are
Okay.
that's what.
No, it was about projective representations and easy introduction for everybody. I took it from a book, Hammersfield, and it was a talk, Hansraj Gupta Memorial talk. It is in Math Student. And also there is a good article on perspective in ILL by Geeta Venkatraman and then by Shobha Bagai also. So I have to get links from Geeta and Shobha. Geeta is there, so she can answer this question.
That was, I mean, it was looking at perspective and art and so on. So, I mean, it was meant for the idea that, you can represent three-dimensional things on 2D and it looks three-dimensional. That was the kind of thing that we were discussing, and it was more about how you could, what are the principles of drawing you use to do something like that. So it was meant for students who didn't have mathematics as a background. So sort of to bring in some amount of mathematics but without scaring them. So it was a different thing. Yeah. Vijay Lakshmi, we need to ask Rekha to talk about her experiences as well.
Let me, yes.
As a woman doing mathematics.
Just wanted to close this formal session first. So are any further questions? I guess no. So Rekha, okay. So Rekha, it's nice to hear this talk. I mean, of course, I am personally pleased to see the application of projective geometry to real life. So now we are open for